Hi folks, Mr. Long here. Today we're going to do a screencast on rectilinear motion, and and if you remember what that is that's motion that goes left, right, or up, down, up, down. It's not two-dimensional motion; it's one-dimensional motion. So really, you have time and distance, and that's it. Those are your only measures. This is going to be a focus on using tables of values and graphs to interpret rectilinear motion, and so let's get going. All right, so here's our scenario. We've got two people. The first person that we've got is John, and we've got Anna, or Anne, sorry, and John and Anne, and they're both on their way to a meeting of the science club. And the science club is at Tom's house. And so what we see here are a table of values for John, and that's the distance. It's the time in hours from leaving his house related to the distance from Tom's house. Okay, so you can see that at 0 time, he's 5.5, and this is kilometers, by the way. So distance is kilometers. This right here is time in hours. So it takes him almost an hour, 0.9 hours to get to Tom's place. So again, that's John. That's John's relationship between distance and time to Tom's place, where the science club meeting is. So Anne's trip is shown here, and again, this is kilometers on the y-axis, okay, and hours on the x-axis. And so what we see is Anne leaving her house here, then the distance is increasing, and then the distance increases. So I think it kind of explains that over here. So she actually forgot her wallet, so Anne had to turn around here and go back home and then do the rest of the walk. Okay, so they both started leaving at 1 p.m. and they had to get there for the start of the meeting at 2 p.m. So let's start going through this. So first question, A. How many kilometers from Tom's house is Anne's house? Let's see. If I notice here, I've got an ordered, so first of all, it's Anne, so I've got to go to the graph here, y equals a of t, okay? Anne's distance depends on time. And if we notice something here, I could put a horizontal line across here because it says that Anne walked for a little bit, then she turned around and went back to her house. How do we know she turned around? Well, the distance was decreasing, and then the distance began to increase to Tom's house. Well, she has to be going backwards because remember, this is rectilinear motion. So they're walking along a single street. Okay, they're not changing direction side to side like east-west. You can assume it's north to south or south to north or something like that. So decreasing towards Tom's house and then reversing and going back towards Anne's house. So if you notice here at 0.6 hours, she's 4.2 kilometers away. That's the same thing as right there. Okay, so that is going to be oh, sorry, that's not the correct calculation. How many kilometers from Tom's house is Anne's house? So it's 4.2 kilometers. I did a different calculation. You'll see that later. So our answer here is simply 4.2 kilometers. Okay, 4.2 kilometers. And let's see. So what is Anne's average velocity for the entire trip? So as soon as it says average velocity, we need to think average is secant, right? That's a secant slope. So I'll just put SEC here. It's a secant slope. And the entire trip, if you look at what's the entire trip? Well, the entire trip would go from right here at 4.2 all the way down to here, which I judged as halfway between 1 and 1.25 hours, so 1.125 hours. So what do we need to do that? We need a secant. What's a secant? It's a straight line connecting two ordered pairs on a graph. So there's our secant, and we need a rise and a run. So let's actually look at the calculation for this one, for rise and run. So remember, and we can go in either direction, but I think it's useful to go to like B. We'll have this value here as, this value here is like our B value. and this is our a value over here, x equals a. So f at b is the y value here, f at a is the y value here. So 0 take away 4.2 is the rise, right? So the y value here is 0, the y value here is 4.2, and that is in, what are the units on that? In kilometers. Okay, and 1.125 hours here, 0 hours right there. And then again, that's in hours, so our units are correct, kilometers per hour. So that's our calculation, rise over run. And then what's the answer to that? Negative 3.73. Why is it negative? Because the distance was decreasing, right? And that makes sense. They're getting closer and closer to their destination. Distance was decreasing. So we still don't have units on that. We need units. So again, that's kilometers per hour. And let's see here. What's the next question? What is Anne's average speed? Well, we know velocity has direction. Speed doesn't have a direction. Speed just is how fast, not where, right? Velocity means the distance is decreasing, in this case because of the negative. But average speed right here, speed indicates absolute value, so we can only have positives. So if the velocity is negative 3.73, let's take a look at what speed is. Speed is the absolute value of the velocity. So it's simply the average of negative 3.73, which is 3.73. Okay, 3.73 kilometers again per hour, making sure we have units. Okay, let's move on. Okay, so here's what we're going to do now. Now we're going to start estimating tangent slopes. So the first question says, estimate J prime at 0.4. J prime at 0.4. So I want to know the tangent slope right there, because that's J, that's for John, right? So at 0.4 hours, what's the tangent slope in meters per second? I've got a bit of a problem here. It's not a continuous function. So I can actually only get secants, right? I can get an average velocity from, let's see, I could do an average velocity from 0.2 to 0.4. I could do an average velocity from 0.4 to 0.5. I could do an average velocity 0.2 to 0.5. Now, if you remember, we get slope from the difference quotient, right? So, or this way, we can think of it as f, again, f of b minus f of a. This is secant slope, right? All over b minus a. Well, what is that? If b minus a is really, really, really wide, if b minus a is a big distance, so think of a curve like this, so if b and a are far apart, that's definitely a secant. But what happens if I make that distance, which we call h, much smaller, like this? So which of those, the first one I drew or the second one I drew, is closer to a tangent? Well, definitely the second one is much closer to a tangent because that distance, b minus a, or we also call it h, is much smaller. So take a look at all the possibilities to estimate the instantaneous rate of change, the tangent slope at 0.4. Again, I could go 0.2 to 0.4, that's 0.2 wide. 0.4 to 0.5, that's 0.1 wide. Or I could go on either side as well, right? There's many options here. And it's not that one is wrong, it's that certain ones are more correct. So our best estimate, and notice the question was estimate, our best estimate is when we keep that distance h or b minus a as small as possible. So it looks like that 0.4 to 0.5 might be best. Okay, so those are our three choices of intervals, just to reinforce that. 0.2 to 0.4 for time, 0.2 to 0.5, that's going on either side of 0.4, or 0.4 to 0.5, okay, for time. So really, again, 0.4 to 0.5 creates the smallest secant, and the smallest secant, or smallest width of the secant, which is closest to a tangent. Oops, daisy. So we're going to select 0.4 to 0.5, the secant that is closest to the tangent, and let's see, what would that make the slope? Okay, the rise is right here, so it's going to go, we're going to go 2.8 is the second y value, minus the first y value, 3.2. Okay, there's your rise. And then your run, b minus a, is just 0.5 minus 0.4. So remember, that's the same thing as x there. That's the same thing as y there, right? So it's -4. And that's that. If you do that calculation, it works out to -4. And again, that's kilometers per hour. And that's our estimate of the tangent slope, j prime at 4. That's how fast John was walking. We estimate at 0.4 hours into his walk. All right, this is where it starts to get a little bit tricky. What does that mean? J inverse at 4.3 primed. Okay, how do we read math from the inside out? So I read 4.3 first, then I write J inverse. Well, if it's J inverse, that means I'm doing the inverse of the John's distance function. So this right here is the y value, right? Because I'm doing an inverse. Remember, x and y switch on an inverse. So 4.3, I have to look at the j function and a y value of 4.3. Right there. Okay, so a y value of 4.3 right up here. And then it's saying, what's the rate of change for j inverse at 4.3? So what does that mean? Let's think about this really carefully. So it means a rate of change, not of distance with respect to time, but of time with respect to distance. Okay, so what it means is we're switching x and y. So normally our slope is in, you can see our slope is normally in kilometers per hour, but the inverse is going to switch x and y, so it's going to be kilometers per hour. So this is saying, what's the rate of change of time with respect to distance when John's distance is 4.3 kilometers from Tom's house, that should say, from Tom's house. Okay, so let's go through and do that. So again, the inverse there means x and y have switched, and it's still, you can do a derivative of the inverse, right? And that's what we're going to do next. So the next question is, what is that value? Okay, what is the value of j inverse at 4.3 prime? Okay, the derivative of the inverse. So take a look at how this table is. It's got time on the top here, right? Time on the top. Time's there. Distance is there for y. If I'm doing the inverse, I need to switch that. Okay, I need to switch that. So that's what we're going to do. Take a look at what we've done. So what I did is moved what was in the bottom row, 4.3. Oh, by the way, I had to get an estimate of the slope of the secant. And in this case, if you notice, well, let's just put the data in the table first. So I had to switch my x and y. So my x became distance, 4.3, and 0.2 is y. Now, to do this, right, these are my x values now here, right? These are my x values. So my x value here is 4.3. So since my x value is 4.3, I switched it, right? I had to look to the left and to the right to see which one gave me a smaller interval. Okay, so which value would I want to use for my estimate of the tangent slope? So 4.3 to 3.2 is 0.9. 4.3 to 5.5 is 1.2. So this gave me a secant that was closer to a tangent, right? Because this is now my run, because I've switched x and y. Okay, so, and again, what's the rise going to be? Okay, these are your y values because we've interchanged them. So I'm doing 0.4 minus 0.2 in the numerator. And then I have to follow the same direction and subtract right to left in the numerator here. Or what's in the top, the x value. So that becomes 3.2 minus 4.3 if you do those calculations. By the way, what would the units be on that? On the top, it's hours. In the bottom, it's kilometers. So that's hours per kilometer. What does that really mean? That at that instant, when John is 4.3 kilometers away from Tom's house, that he's reducing his trip by he's reducing his trip by 0.18 hours every kilometer he walks. Okay, so that's the first part of this question. I'm going to take a look at a couple more questions that are related to this in a follow-up screencast.